Okay, so now let's talk about independence and basis vectors. So we said vectors x1, x2 all the way to xn are independent if for any scalar a1, a2, an, the linear combination of these vectors is 0 if and only if the all the scalar is 0. And they are dependent, of course, if at least one of the scalar is non-zero. What I mean by that is, for example, let's take a case of x1 and x2. We have two vectors. We say that these two vectors, x1 and x2, are independent if, for example, you have c1 x1, c2 x2 is equal to 0 if and only if c1 equal to c2 equal to 0. So if, for example, what does it mean intuitively? So let's say that this is x1, right? If x2 is this, it's in the same direction, but it's just different by a scalar constant, right? In that case, x1 and x2 are dependent because you can just multiply x1 by a constant and then you get x2. So this expression, let's say this is 1, can be 0 for some c1 and c2. But assume that x1 is this and this is x2. There is no way you can multiply x1 and x2 by constant to get the result to be 0. And we say x1 and x2 are independent. Why do we need that? We need it in terms of matrix vector language. So we say that, remember the definition I had for a matrix vector product? And I said that definition is very important. We define y equal to ax. We define y to be as a linear combination of columns of A. So we define it to be x1, a1, x2, a2, all the way to xn, an. So here A is referred to the columns of A. Now, if you consider this equation of y equal to ax equal to 0, if this equal to 0 has only the solution of x equal to 0. X equal to 0 means what? Means x1, x2 all the way to xn equal to 0, right? This means that the columns of A are independent. So if the linear combination of columns of A is equal to 0, only for the case that the column vector x is equal to 0, this means that the column space of the column of A are independent. Another way to look at that, if ax equal to 0 only has a solution of x equal to 0, this means 1, column of A are independent, 2, A has trivial null space. Since x equal to 0 is the only vector that gives ax equal to 0. Now let's talk about the basis vectors. So we said that if column of A are the basis vectors for the m-dimensional space, what I mean by the m-dimensional space means that we have m rows, right? What does m-dimensional space, for example, for vectors means? So let's say that we have a vector x. This means that we have x1, x2 all the way to xm, m rows. Then A, so what does it mean? First, we have to know what is the definition of a basis vector. The basis vectors are the vectors that are first independent. So basis vectors independent. There are a set of vectors that are independent. 2, they span the entire subspace. They span the entire subspace. Okay, so if columns of A want to be the basis vectors for m-dimensional space, this means that we have m rows, right? Then they have to be independent. So according to one definition, they have to be independent. Okay, so linear combination of the column is equal to 0. This means that the vector x is 0. Okay, but they have to also span the entire subspace, the m-dimensional space. then it means that how many columns we should have. So let's name the column A1, A2, all the way to how many columns should have? If you have, this was an important theorem for a basis and independent, right? This means that you should have exactly m columns, right? If you are in m-dimensional space, you can expand the entire subspace by m vectors, right? So let's assume, for example, in the case of 2D, you are in 2D, in a Cartesian, for example, let's say you're in 2D. If you only have one vector, you cannot expand the whole subspace, right? So for example, you have this vector and you want to make this vector. There is no way you can multiply this vector by a constant or a scalar to get that vector. By two vectors, you can span two independent vectors, of course, you can span the entire subspace. Right? If you have three, one of them is dependent on the other one. So one of them you can write it as a linear combination of the other two. So if the columns of A want to be the basis for an m-dimensional subspace, this means that these columns must be linearly independent, and the number of columns should be equal to m. Therefore, A has m columns and m rows. So A is a square, right? So here I explain that A must be a square matrix with linearly independent column. And of course, any m-dimensional vector can be written as a linear combination of columns of A. This means that if this B is any vector, any m-dimensional vector we have, therefore AX equal to B has a unique solution, right? So if columns of A are independent and they form a basis function for an m-dimensional space, then if B is any vector, m-dimensional vector, B1, B2, all the way to Bm, then equation AX equal to B has a unique solution. Another way to look at it, again, go back to the definition of matrix vector product. A1, what is this? It's the columns of A. A1 times x1 plus A2 times x2 all the way to AM times xm equal to B. But remember, the columns of A1 all the way to AM, they are basis vectors. So they are independent. First they are independent, then they span the entire m-dimensional space. So you can find the coefficient x1, x2 all the way to xm that gives the linear combination equal to this B. Okay, cool. Now let's talk about the complexity, number of flops. So usually the complexity of this matrix of vectors, actually the challenge is pretty easy. Only the challenge is coming from the sparse matrices. So we're going to talk about that right now. So now assume that matrix A is general matrix, m by n matrix. Then addition, scalar multiplication requires mn flops. Why? We talk about the A plus B. If A is m by n, B must be m by n, and the result, let's say C, is also m by n. How many elements we have? Mn. How many multiplication? How many addition we have? One per each element, one per each entry. So we have mn multiplication, addition. Therefore, we have mn flops. A scalar multiplication, we talk about that C times A. We multiply this C by each component of A. How many elements we have? Mn. How many multiplication we have? Mn. So we have Mn flops. A transpose, we talk about that. It has a zero flop. Swapping rows and columns is considered as no flop. So now, what if at least one of the A or B is a sparse? Now, remember, this is very important. For a sparse matrices or sparse vectors, we talk or we work with a concept called NNZ, number of non-zero elements, right? Because adding or multiplying by a zero is considered as a no flop or as no extra flop. Okay, so that's what I wrote here, since there is no flop for addition or multiplication by zero. So it turns out the number of flops when you add A plus B is at most or at maximum is equal to minimum number of non-zero element of A and number of non-zero element of B. Right? What's the idea behind this? So for example, assume y is at most. Assume a is equal to this 1, 2, 0, 0. Assume this is a sparse, right? Let's consider it like a vector, for example, because vectors are like matrices, especially if they're matrices. And b is 0, 0, 1, 2, 3, 4. When you add a plus b, how many flops do you have? 0, because they don't have an overlapping, or they don't have any pattern of overlapping non-zero elements. So if a and b do not have overlapping non-zero element, then a plus b has 0 flop. And that's why it's at most equal to that. And then at most is equal to the minimum number of non-zero elements of A and number of non-zero elements of B. So for example, here it would be maximum equal to what's the number of non-zero elements of A, and then z of A is 2 here, and then z of B is 4. So this is going to be A plus B has at most 2 number of flops. And if they don't have an overlapping number of non-zero element, then it has 0 flop. So we can define it based on a bound, right? So the number of flops of A plus B is less than or equal to minimum NNZ of A and NNZ of B. And that's sufficient for us for complexity. We are talking about the big O notation, right? So it's less than or equal to this quantity. Okay, so that's for the addition. Now let's talk about the matrix vector multiplication. So assume general again, A is n by n, and x is n by 1 vector. So when you multiply A by x, what do we do? Let's consider another definition we have. Definition of a dot product. We calculate the ith component of y to be equal to the ith row of dot product of ith row of A and the column vector x. So why do we want to use this definition? Let's see. So this is A11, A12, all the way to A1n. This is AM1, AM2, all the way to AMN. Right, no, that's not 0. This. Okay, and then we have x1, x2, all the way to xn. First of all, it's very important to know what is the dimension of y, because you want to calculate for all the value of the y, y1, y2, yn, all the entries of y. So x is n by 1, a is n by n, y is n by 1. Okay, so we want to calculate m entries. Okay, m entries. Okay, so let's see for each entry how many calculations we need for each entry. So let's take the ith row of y. So ith row of y is equal to the dot product of this ith row of A by this column vector x. So how many products we have? As many as number of elements, right? How many elements we have? AI1, AI1, all the way to AIN we have n, right? We have n. I can write it down even. AI1 times x1 plus AI2 times x2 all the way to AIN times xn. Remember, we have n columns. So how many products we have? N. How many addition we have? N minus 1, right? So we have n plus n minus 1. How many elements we want to calculate? M of them, right? So because for each yi, we have this many n plus n minus 1. We have m yi. So in a sense, we get this one, and it's going to be estimated by 2nm or something like this. Okay, good. Now, what if A is sparse? So what if A is sparse? Then in that case, one way to look at these, again, write this definition. Yi is equal to the dot product of the iter of A and the column vector X. Now, for sparsity, we have this number of non-zero elements because most of the entries are zero. So we have assume we have m non-zero element. Assume A in general has m non-zero element. A has n and z of A equal to m. This is better, write it like this. Okay, good. But A has m rows as well. A has m rows as well, right? Row 1, 2, all the way to m. And the number of non-zero elements, let's say, is equal to m, right? Or let's say that let's not even associate a number to that. Let's call it n and z. We have number of non-zero elements to be n and z. And so how many number of non-zero elements we have per row? We have n and z divided by m, right? We have m rows. In general, we have n and z of A. So on average, we have n and z divided by m as a number of non-zero elements per row. Okay, so that's what I wrote here. Now we can go ahead and apply that the same definition as we have here. This is the definition that I'm talking about. So we have n and z of A, n and z of A, n and z of, this should be A. Right, over m minus 1, and then we multiply by m. Remember, when we get a 0, when you multiply 0, it's not a flop. So we are bounded by n and z, right? So if x is 0 or non-zero, doesn't matter. If the rows, for example, contain some zeros, when you multiply by x, let's say you multiply this one by x, and this is not a flop. You multiply this one by x n minus 1, this is not a flop. You multiply this one by x n minus 2, this is not a flop. So you only care about the number of non-zero elements of A. And we consider general case of A, actually. Okay? So this one will be 2n and z of A. Why do I mean by that? If you add them up, just ignore this one, you get 2n and z of A divided by m. You multiply m, you cancel out, you get 2n and z of A. Good, so that was a general case. Now, what if, let's say, A is diagonal? If A is diagonal, then the number of flop is n and z. The diagonal is the special case of the matrix we can have, right? Because if the A is a zero matrix, then we have zero flop. So let's consider the next sparse case. Let's consider, for example, the diagonal matrix, right? If you have a diagonal matrix, then the number of flop. So you have a diagonal matrix here. This means that the elements on the main diagonal is non-zero and all other elements is equal to 0. So by the way, the elements on the main diagonal, when I say is non-zero, the main diagonal elements also can be 0. In general, we consider non-zero element. So we can, for example, this is an example of a diagonal matrix, 1, 0, and all the elements is 0. This is also a diagonal matrix, right? So in general, for a general case, we consider the elements of main diagonal is non-zero and the elements of diagonals are all 0. So let's consider general case. Assume A is a diagonal matrix and assume the number of non-zero elements is n and z of A. Okay. So what is the number of flops that we need in that case? The number of flops, perhaps here we can go ahead and calculate this AX with each other. Let's use a definition that we have for, we can use either definition. Let's use either definition. So for yi, you calculate this aik times xk. But wait, in each row, we have only one in each row, right? In each row, we have only one. Isn't that correct? In each row. In each row we have only exactly one. So how many one we have? As many as number of non-zero element of A, right? So you might want to say that A is a diagonal matrix, so is n by n. For example, you might have n non-zero element. But as I said, for example, let's consider general case, because some people can say that, hey, for example, I can have this A1100. Let's consider general case, n and z of A, number of non-zero element. Then here, number of non-zero element is 2. Here, the number of non-zero element is 1. The number of non-zero element can be n. So if you consider general case that we have number of non-zero element of A to be n and z of A, then yi, ik, aik times xk, this one is either 0 flop, because all the elements, the whole row is 0, or it's gonna be 1 flop, or at most 1 flop, or at most 1 flop. So let's say aik is 1, right? And xk is whatever, is also non-zero. So it's gonna be 1 flop. When you multiply it, it's gonna be 1 flop. If one of them is 0, it's gonna be 0 flop, right? Just add them all together now. So for each iteration, it's gonna be either 0 flop or 1 flop. If it turns out that, let's say x is a general vector, and then A is exactly diagonal, that all the elements on the main diagonal is non-zero, then you're gonna get n and z of A to be the size of A. It's gonna be the number of rows of A or number of columns of A. Otherwise, we just show it as n and z of A. So in general, the number of flops for a matrix vector operation when the A is sparse is the number between n and z of A and 2 n and z of A. And the reasoning is exactly the same. So you're gonna go first, consider a general case that you have n and z of A, number of non-zero element for a general matrices, right? And you have m rows. You just say that without loss of generality, assume we have n and z of A divided by m non-zero element per each row, and then you calculate this matrix vector operation, and then you can say that, okay, we have the sparse vector 0 vector, which has a 0 flop, right? But I can consider 0 vector as also a diagonal matrix, which the n and z of 0 vector is 0. So what if I just consider diagonal matrix with a non-zero element to be n and z of A, and then just go ahead and calculate this this expression, and then count the number of flops. So the minimum you get is an n and z of A, and the max you get is a 2 n and z of A. Okay, so that's it for this video. I thank you so much for watching this video. In the next video, I'm going to talk about the linear equations and the system of linear equations. Thank you so much.